Hey everybody, it's Ripley again. Man, we're moving now. We're going to talk about confidence interval, which is out of chapter 7. Okay, now we need a little bit of background here real quickly. We're going to talk about something called a point estimate. All right, and I'm going to teach you how to build confidence intervals and why we build them the way that we do. A point estimate is really simple. It's simple. Just a minute. Sorry, one thing at a time, Ripley, one thing at a time. It's a single data value. All right, it's a single data point or statistic, point or stat. Let me give you an example. If I take the ages in a room full of kids and I say X bar, that's our mean, right? So it would be the average age. This is a point estimate. This is a point estimate, all right? Because it estimates mu. All right. Now, the reason that it estimates mu, if you remember, is that the means are unbiased estimators. Remember, we got into sampling distributions, we got into the central limit theorem, which is super powerful. But what it really told us is that I know that sample means have a tendency to accumulate around the true population mean, which is our parameter. So that's why we call that an unbiased estimate. Other examples of unbiased estimates are things like p hat. Now this is, we've talked a little bit about this. This is our sample proportion. Sample proportion. Remember, this guy's an unbiased estimator because it too accumulates around a true population proportion. It is also a point estimate. This is a point estimate, a sample mean, a sample proportion, and then S squared, which is we know that this is the sample variance. Sample variance. Whoops. Whoa, what's going on here? All right. Now, this is also a point estimate for the variance of the population. In other words, if you have an unbiased estimator, then the point estimate is just a sample statistic like a mean, a variance, a proportion, etc., that we can use to best estimate the population mean, proportion, variance, etc. All right. Now, what we're going to talk about is we're going to talk about confidence intervals around proportions. All right. So confidence, I'm going to start abbreviating this as CI around, and here's why proportions. They're everywhere. You see them all. Pick up any newspaper, open up any web page, any news article in the web page. If you go to Reddit and read anything, you are going to be absolutely blasted with proportions. 25% of all Americans believe that Romney is a blah blah blah. 87% believe that Obama is a blah blah blah. So particularly now, you're going to hear percentages thrown at you everywhere about the presidential candidates. All right. Now, what they're doing is this, and this is really important that we get our brains wrapped around. They go out and they sample people. So let's say that they take an N of 5,000 people. And let's do something non-political. Let's say dog owners, all right? Do you own a dog? So we want to figure out the percentage of people that own dogs, okay? So X, N is our sample size. Let's let X equal the number of people that own dogs. So it's kind of a binary setting, or a binomial, setting, also binary. You either own a dog or you don't. All right, so let's say, just to keep it simple, let's say that 4,000 people own dogs. That implies that my sample proportion is 4,000 divided by 5,000, which is 0.8, or 80%. Now, this is my point estimate. Now, this may or may not be accurate. In fact, since it's made up, it's most likely not accurate, and I wouldn't say that 80% of households own dogs. However, it's the best estimate that we have because it's a point estimate of an unbiased estimator. All right, this is an unbiased estimator, so we know, especially as N gets really big, we can start getting really confident that we know what we're doing, that we're getting a value that we can be confident in. And that's the reason that we talk about these as confidence intervals. Okay? All right, so here's the problem, though, is we know almost for a matter of fact, even if this number were huge, we know that this is probably wrong. Probably, even if it were, think about it this way, if 79.3% of all American households had a dog, this would still be wrong. 0.8 is not equal to 0.793, right? So what we have to do is we're going to take our p hat, our point estimate, and we're going to set this in here. We're going to build an open interval. Hopefully you remember this from your algebra. We're going to build this open interval that's going to have an error statement in it. So we're going to take our point estimate, which is our sample proportion, and we're going to add an error. That's how far we think we're going to be off. All right? And that's how far the mathematics is going to show us that we can be confident in building this interval around so that we have a certain level of confidence. And we're going to take p hat and we're going to subtract. Whoops. And we're going to subtract that error. Remember, E is just error. All right? And we're going to develop this error together right now. I'm going to show you how to develop this error. But this guy right here, when everything is said and done, this is called our confidence interval. This is my CI. All right? So what you do, if you think about it just really, really simply, and for those of you that have played around with in your calculus classes when you're trying to deal with tolerances or error bounds, this is a real common practice. We simply figure out a point estimate, booyah, and then we figure out an error, and we say, okay, if I take the point estimate plus or minus that error, that's going to give me an interval. It's just an open mathematical interval. Think about it this way. If you think about it on the real number line, if I grab any real number on the real number line, which I'm just going to call p hat, and I go out plus or minus error. So if I go plus error, so this is going to be p hat plus e, and if I go minus my error, this is going to be p hat minus e, what I have is an open interval. All right? And that, again, is what we call a confidence interval. Now, before we start building these mathematically, let's talk about what they really mean. All right? And I'm going to do this in complete absence of mathematics at all. We'll just do this theoretically for a second. Okay? All right, so let's say that I go out and I do this little survey right here. This is my dog, right? I guess this down here. This is my dog survey. Again, I don't suppose that it's accurate at all. However, what I'm going to, through mathematics, I come up with something that's called, let's do a 95% confidence interval around the true proportion or percentage or fraction, call it what you will, of dog owners or households that have dogs, okay? And let's say, just for giggles, let's say that turns out to be, let's say that our error is plus or minus 3%, all right, which is the same thing as plus or minus 0.03. Now, what that means is, what that implies, is that my confidence interval is going to be from 0.77 to 0.83. All right, remember the way that we get this is we simply go 0.8 minus 0.03 and 0.8 plus 0.03. All right, now what does this really mean? Now this is a biggie. Remember, we're going to take a deep breath here. In fact, I'm going to take a drink of water. I think everybody should have a drink of water because it gets real easy to get confused. Why is sample proportion an unbiased estimator? Well, because the law of large numbers tells me, the law of large numbers tells me that if I were to replicate this study over and over again, all right? In other words, if I were to create sampling distributions of size n equals 5,000 in the United States, okay? And I were to ask the question, does your household own a dog? Over and over and over again. Remember, I would get p hat 1, I would get p hat 2. These are sample proportions that are coming out of my sampling distributions, right? And I were to do this a whole boatload of time, which, remember, a sampling distribution is the set of all possible samples of size n equals 5,000, right? I know for a fact that if I took the average of all of these, of all of these point estimates, that these guys, I'm going to call these p hat n's, would turn into the population proportion.